My name is Emily Montoya, and today we're going to be talking about underground storage tanks. So first we need to understand what an underground storage tank is. An underground storage tank is any tank, including its piping, that has 10% or more of its volume stored underground. They're normally made of steel with a protective coating, but can also be made of fiberglass, and they commonly store petroleum, and they can be found at gas stations. So the EPA has the authority to regulate underground storage tanks. The EPA only regulates storage tanks that contain petroleum and other designated hazardous substances. Other storage tanks are regulated at the state level. And by law, all underground storage tank contamination releases must be taken care of. So they evaluate the extent and degree of contamination, and then they hold whoever is responsible liable for remediating that site. So why are leaky underground storage tanks an issue? Well, they are the biggest contributing factor to groundwater contamination. So in the photo you can see that when the petroleum leaks out of the storage tank, it goes into the aquifer, which contaminates the groundwater, and then in addition to that, the gasoline vapors also contaminate the soil. This is an issue obviously because it's harmful to human health and the environment, and those materials are very hard to get out of the environment, so we don't want them in there if we can avoid it. So the biggest causes of leaks include corrosion, faulty installation, and inadequate maintenance. And this photo shows an example of corrosion. So you can see the holes in the tanks. That's what happens over time when the chemicals eat through the steel, and then whatever's inside of them comes out of them into the environment. So a very important aspect to maintaining these tanks is preventing the corrosion that we just saw on the last slide. So one of the things they do for steel is they coat all of steel tanks with a protective coating to try to prevent corrosion, but a better way to do it is called cathodic protection. So as you can see in the image on the screen, it's an electrical system. So corrosion is an electrochemical process, so we can use electricity to kind of counteract it. The system contains a power source, which is the rectifier up top, and then the pipeline structure in the photo is the tank that's being protected, and then we have the anodes. So the anodes are made of a material, usually magnesium or zinc, that has a higher corrosion potential than steel. And what that does is it causes the electrical current to flow in such a way that the anodes corrode instead of the steel tank. And it's great if the anodes corrode instead of the tank, because we don't care about the anodes. They don't have any harmful substances in them. So that's one way that's very commonly used to prevent corrosion in tanks.
Hi everyone, my name is Doyle, and I'm going to be talking about the causes of leaks and some of the different effects of that. So you can see in this diagram here that piping leaks are one of the biggest causes of leaks. You can think about piping as one of the largest problems because of the fact that the piping has to run from the tank itself to above ground, and then there's also a lot of piping that exists underground to get from one source to another. So there's a lot of issues associated with that. Pipings, any bends in the pipes can have a lot of leak potential there. And then you can see spillover and overfill is the next largest percentage at 22%. So this is essentially an oversight issue. When you don't regulate and understand how much is already in your tank and you overfill it, or you're not paying attention and you overfill it, then that leak happens on the surface, and that can leak down into the soils and potentially into the groundwater if the leak is large enough. And then you can see tanks represent 5% of the causes of leaks. This is primarily from old tanks that were made of steel. They would corrode very easily, as Emily talked about, and then leak. And then you can see there's unknown causes. Next would be dispenser. Dispenser leaks are primarily caused by the corrosion from acetone. If that's being stored, it can corrode the seals of the dispenser and cause it to leak. And then joint leaks are a major issue. Think about any time you have two pieces coming together, they need to be essentially air and water tight to be able to hold those materials within the tank. So leak detection is very important because not only, you don't want to find out that you had a leak by having an environmental catastrophe or health issues in your community. So in order to prevent leaks, you want to be able to detect them so that when there is a leak, you stop it as soon as possible. So secondary containment with interstitial monitoring is the most popular type of leak detection nowadays because it's required by the EPA. But there's also vapor monitoring wells and groundwater monitoring wells that are also used in order to prevent leaks and detect leaks that are existing. And then there's different types of probes that can be inserted into the tank to be able to monitor the level of the liquid, to be able to monitor just by pure volume whether or not you have a leak. So secondary containment, this is my very basic diagram of what that looks like. So you can see the orange here and this black line represents the primary tank. This would, in the past, this would have been all they had. So now we add a secondary layer shown by this blue area and this black line here in order to seal that tank one more time and protect it even further. And then within this open space here represented by the blue, you have an interstitial monitor that exists. So if something does leak out of this primary tank, it is collected within the secondary tank, and you can see that leak using the interstitial monitor and be able to detect that. And then this monitor is placed down at the bottom of the tank so that if something does flow out even up here, it'll leak down and eventually reach the monitor. So it's in a strategic place so that it can detect leaks. So the tank gauging systems, this is the type that I mentioned where it's just done by pure volume. So there's various different types of gauges, one of which shown here is a radar level gauge. So this is pretty cool high tech. You can use a radar to detect where your liquid's at in the tank and be able to say how much your volume is based on that. And it will give you a graph kind of like this. And then you can also use multi-point temperature gauges to say where the liquid's contained. And these can be anywhere from very simplistic, it's just a number on the top of the tank where you could go out and read it physically, or they can be connected to systems that then can be sent to computers so you can monitor levels off-site or wherever you want to be. So our world's all interconnected at this point, so even your tanks can be interconnected. So vapor monitoring is important. As Emily mentioned, the vapors can exist when there's a spill, both the liquid itself and then the vapors can contaminate soils. So vapor detection is one way that you can detect a leak. So there's a couple different ways that you can detect or that you can install a vapor monitor. You can either drill a well or you can bury the monitor within the soil itself, and the monitor will be able to pick up any leak that's in the soil. Further, you can do vapor monitoring by taking soil samples. Those samples traditionally are sent to labs, but depending on your field crew, you might be able to analyze them out in the field for the vapors that you're looking for and see if you have any leak that way. And then groundwater monitoring. I find this is the most important because we are most closely connected with leaks via groundwater. We do not want our groundwater contaminated. And so being able to monitor the groundwater for leaks is very important because it will give you an idea of if that water is safe to drink. So a well is drilled nearby the tank so that if there is a leak, it'll be detected as soon as possible. And then that well can either be monitored by hand on a month-to-month basis by withdrawing water and sampling it in the field or in a lab, or you can put down a gauge such as you had with the vapor monitor and detect it on essentially a minute-by-minute basis to ensure that your groundwater is intact and safe.
My name is Daniel Chavez. I'll be talking about the treatments. As the girls have mentioned, we have all of these great safeguards now in place as new technology has been developed, but what do you do when you come across a contaminated site that didn't have all these? And so today we'll be covering soil and groundwater remediation techniques that are used both in place and once the soil is excavated. So we'll be talking about biological, physical, chemical, thermal, and some new technologies that are also out there. And so as these treatment processes are driven is basically by what was in that tank and how long it's been leaking. So again, these are typically cascade treatments, so you'll have one treatment driving another, driving the next one, and until you reach remediation. And these are long, long projects, so typically they last 3 to 5 years, plus they can go over 10. So we'll talk about in-place biological first, and I'll just cover a couple of these. For soil, we'll go over bioventing. So again, this is just the addition of turning on a fan, introducing oxygen and nutrients into that soil, and allowing microbes to eat away at all those contaminants. Again, you're going to have a grid of wells set up around that to monitor your progress on that and how far they've come along. You're going to be using a geoprobe, similar monitoring techniques as Maddie had mentioned. For soil and water, we'll talk about phytoremediation. That's essentially, guys, just using green technology to plant trees, plant sunflowers. I've seen this done with sunflowers where it actually absorbs hydrocarbons in the soil and uses it within the system and treats it, and goes through the whole process. And it's shown that these sunflower treatments can actually clean up faster than groundwater monitoring or pump and treat or anything of those technologies. So for chemical physical SVE systems, as a lot of you saw on the field trip with Dr. Brown, SVE systems reverse the fans. Essentially, you're going to be pulling all those vapors out now and pulling all those contaminants out, and then sending it through an air stripper. Picture right above there. It's kind of an odd picture, but essentially you're sending all those vapors up through there and hitting that with water and taking out those contaminants as they settle out. Air sparging, that's going to be, again, introduction of oxygen into the system to blow out those contaminants through the water. And for soil and water, you can go through a dual phase extraction, which is essentially sucking all of that air back up through the water table and the soil. And you take a specially designed well, very costly, but also very effective. So once you excavate that soil, what can you do? So for non-excavated, you can do the land farming. So this is actually a bioxide tank that's pumping bioxide down into the system and giving the microorganisms nutrients and allowing them to essentially degrade the system. And then of course this has an extraction well that's right behind there that's going to be pulling back out that clean water, or pulling out that bioxide. And then for water, you're going to have wetlands. These are constructed, you'll see these all over the place in soil treatment. Sewage treatment, and essentially that's just going to be using, again, just settling technology and green technology to settle out those contaminants and treat them effectively that way. So out of place again for soil. Once you have all of this excavation done, how are you going to pull the contaminants out of that soil? So you can use a solvent such as hexane to pull contaminants from the soil. It's either done in a reactor or open. Those reactors are going to need secondary containment, as well as your open are going to need extra secondary containment because they're going to be open to the environment, to rain, to machinery, everything else. And for waters, this is actually a GAC system right here that is treating for TCE. And the reason we use carbon is it's very porous, has a huge surface area, and it's able to treat a number of contaminants. So new treatments. Algal. This is a up and coming technology that is actually utilized for its essential fact that it can produce a byproduct that you can actually sell later down the road. It's mobile. You can treat for metals, phosphorus, nitrogen. Essentially, they're treating actually tertiary sewage treatment water with this now, and so again, it can be a beneficial use of that contaminated water and also give you a byproduct out of there too. Again, that's going to cover our presentation on underground storage tanks. Thank you all. Our references are listed below here, and thank you.